In this lesson, we will dive deeper into the discussion of maximum and minimum values associated with the integer family of data types, focusing mainly on the byte data type. We'll start with a quick discussion on how these integer values are stored in memory, specifically as strings of bits, using this Java program to help you see what's going on. This Java program assigns a value to a byte variable, outputs it, shows a row of 8 stars, converts the byte value into a string by calling this specially defined static method, which returns the desired 8-bit string, which is then output. Later we'll include these several statements to show how the complement of the value appears. We'll start with the value 0 as a byte. When we run it, you can see the value outputs normally, and then again as a string of 8 bits, all 0. This is how a byte is stored, in a row of 8 bits. In the row of 8 bits, each has a place value in base 2, with the rightmost place, just as in our number system, having a place value of 1. The next place value to the left has a value of 2. One more place over has a place value of 4, then 8, 16, 32, and 64. Those 7 places are the ones used for byte data values. Now you're probably thinking, what about the next place? Good question. That place, that bit in the leading position, is used to indicate the sign of the number, whether it's positive or negative. This is called the sign bit. If the sign bit is a 0, this means the value is positive. If the sign bit is 1, the value is negative. There is a whole system based on this called 2's complement, but that is a lesson for another time. Let's change the value of num1 to be 1 and run the program. Notice a 1 shows up in the ones place of the string of 8 bits, which is correct. We change the value to 2, and now there is a 1 in the 2's place. We change it to 3, and now there are 1s in both the 1 and 2 places, which adds up to 3. Let's change it to 6. What is the bit string now? Well, there are 1s in the 2 and 4 place, whose sum is 6. This is how you get all the different values. For every 1 in a place, just add up the value of each place to get the actual number. Let's try 10. You can now see 1s in the 8 and 2 position, adding up to 10. Let's try 31. Here you can see 1s in the first 5 places, which means 1 plus 2 plus 4 plus 8 plus 16, which equals 31. Now let's jump to 127. What is the bit string for this value? Well, you can see 1s in all the 7 places after the leading sign bit of 0. This indicates the positive value 127. This is the largest possible value that can be stored in a byte. There is no more room to go higher. Now let's talk about negative values. For every non-negative value, such as 0 or 1 or 2, 6, 10, 31, or 127, there is a corresponding negative value called a complement. The complement of a non-negative value is kind of like a mirror image of it, an inverse value. The complement of 0 is negative 1. Imagine a boundary between 0 and negative 1. And as the values increase on one side, they decrease on the other. We'll uncover these next few code statements in our program to show this idea. We assign 0 back to num1 and then use this special operator, the complement operator, cast it as a byte, and assign it to num2. The cast is necessary because the complement operator generates an int value, which is 32 bits, and it needs to be a byte of 8 bits. When the program is run, both values show up, and you can see the bit strings are exact inverses of each other. For every 0 in the first string, there is a 1 in the other, and vice versa. This is how integer-type values are stored in memory. We change the first value to 1, and you can see the complement of 1 is -2. And you can also see how the bit strings are again exact inverses of each other. We change the first value to 2, and you can see the complement is -3. Bit strings exactly inverted. What do you think would be the complement of +10? If you thought -11, you are correct. Let's see the program do this for you. An easy way to think about the complement of a value is to think of its opposite and then subtract 1. Let's try that. What is the opposite of +1? If you thought -1, that's correct. Now subtract 1 from that and you get -2. What is the opposite of 10? Well, of course, it's -10. And when you subtract 1, you get -11. This works the other way as well. If you want the complement of a negative value, follow exactly the same 2 steps. Opposite, then subtract 1. For example, for the complement of -11, think the opposite of -11, which is +11, and then subtract 1 to get 10, which we already know is the complement of -11. The values 10 and -11 are complements of each other. Now let's go back to 127 and see what its complement is. Can you think it? Pause if you want to think of this value. Okay, let's try it. The complement of 127 is -128. Opposite, -1. And you can see the bit strings again are exact inverses of each other. Now that you have seen how these are stored, with the sign bit being 0 or 1, indicating positive or negative, and the rest of the bits adding up to the actual value, what happens if you try to step out of bounds, force a larger value into a byte that it can't handle? Let's add a statement to our program after assigning 127 to the byte variable. And now we'll increment the value of the variable by 1 and run the program again. What do you see now? Well, the variable that started as 127 and then was increased by 1 now shows a value of -128. How can this happen? Well, that is what the compiler does internally. It just wraps around to the other side when you exceed the natural range of the value. In fact, this is what this phenomenon is called, wraparound. The maximum value of a byte, when exceeded by 1 or more, wraps around to the other end of the range, to the minimum values. Let's exceed it by 2. Same thing happens, but 2 steps beyond. What if we assigned -128 to start with and subtracted 1? Will it wrap around the other way? Yes, it does, as you can see in this example. So now you have seen how integer-type values are stored in strings of binary digits called bits, how different combinations store different values, how the leading bit is a sign bit, how complement values have inverse bit strings, and finally, how attempts to step out of bounds cause the wraparound issue to happen.